Well, thank you. First of all, thank you very much for the invitation. It's really a pleasure to be able to give a talk at this wonderful seminar. So I will talk about how to represent the solutions of total variation regularized problems. And it's quite related to Michael's talk, since we're trying to obtain similar results, but for different energies. And let me mention that this is a joint work with Claire Boyer, Antonin Chambol, Johan de Castro, Frédéric de Gournay, and Pierre Weiss. So first, I recall a few known results about how to represent the solutions of variational problems in the space of random measures. Michael has already mentioned some of them, so I'll be very quick about that. And then I will generalize it to variational problems involving convex regularizations. And eventually, we will deal with the case of functions with bounded variation and to see how it applies to image processing. So this topic of trying to represent the solutions of variational problems is quite old. In fact, for many years, mathematicians have tried to describe this kind of solutions. And I must say that in signal and image processing, there is a, well, Michael had a huge influence by really highlighting the importance of that fact, especially when working with spaces of measures. So I became interested into this topic when I was working on similar problems as him. Namely the basis pursued from measure. And so what is it exactly? Well, you're given a compact domain and you're trying to recover a random measure, but you only have a few linear measurements that are given by integrating this measure against continuous functions. So you have m linear measurements and you want to find the measure which has the least total variation among all the measures which provide you these linear observations. So the total variation, Michael has already talked about it. It's really the generalization of the L1 norm. It can be defined by this duality formula, for instance. And it's been considered in the last few years by many authors in signal and image processing, after the works of De Castro and Gamboa, Bredis, Pikkarainen, and Candes and Fernandez-Granda, for instance. It's been used for deconvolution, frequency estimation, super resolution, but it's quite old energy that has been used for many years, at least since the works of Krein and Berling in the 1930s, who were using it for theoretical purposes. And curiously, this kind of models provides us with some of the oldest examples of representer theorem that I am aware of, at least. There's a result by Zurwicki in the 1940s, which tells us that there is a solution to this basis pursuit problem that has the form of a sum of at most m Dirac masses. Later on, this result was refined by Fischer and Jerome in the 70s, and they noticed that all the extreme points of the solution set are actually of this form of a sum of at most m Dirac masses. So that's quite interesting if you remember what an extreme point is. That is the points of a convex set that cannot be written as a convex combination of other points of this convex set. For instance, in this picture, you have E0, E1, E2, E3, E4, and all the points, the red points on that arc of circle. Well, these extreme points, they are important because of the Krein-Milman theorem, which tells you that you can reconstruct the whole convex set by simply taking the closed convex hull of the extreme points. So in some sense, if you are able to find all the extreme points of the solution set of your variational problems, then you have access to the full set of solutions. So you simply need to look for the solutions which are m-sparse. Let me also mention that actually Fisher and Jerome were working on a slightly more general model where you have a differential operator that is involved, this operator L, which maps some functional space onto the space of measures. And they consider this kind of models, which are a bit more elaborate. And these results were generalized by Michael and collaborators, and also Flint and Weiss recently. But I won't go into the detail about these more sophisticated models. It's just to give some intuition about what we can get using representer theorems. So what are the consequences of this representation results? First of all, you have some intuition on the theoretical side about what you do when you regularize. What we can understand from these examples is the fact that the total variation norm tends to promote Dirac masses. But you also have consequences on the numerical side, because you have some information on the structure of some solutions, so you can exploit it in some algorithm. In particular, you cannot encode any random measure on your computer, but you can encode the measures that are M-sparse. You simply have to encode the amplitudes and the locations of the Dirac masses. So you can encode your measure efficiently. You can also bound the memory footprint, because you know you don't have an infinity of Dirac masses to store. And then you can put this into some adapted algorithm, such as the conditional gradient algorithm that was promoted, for instance, by Predis and Pikkarainen into this in this context. And you can design efficient algorithms for solving variational problems in the space of random measures. If we want to extend this to other functionals, what are the key ingredients? First of all, our goal is to find a representation of some solutions of our variational problems as a sum of a few atoms. There are many such results in linear programming, semi-definite programming. These have been known for years, but it's especially important in our signal and image processing area since we want to be able to tackle infinite dimensional problems. I have already mentioned the work by Predis and Pikkarainen. There are many papers about this which take advantage of these representations to solve these infinite dimensional problems on a computer. And let me mention that while we have, in most works, we deal with static measures, there are also extensions to the dynamic case, especially in the work by Predis and Fenzo. So the key observation to extend this kind of property to more general energies is the fact that the Dirac masses, as Michael mentioned, are the extreme points of the total variation unit ball. So that's the key observation if you want to extend this problem. And to state the general problem, the general theorem, we need to remind about what a face is. So a face of a convex set is simply a convex subset, such that whenever you're able to describe your point as a convex combination of x1 and x2, then the whole opening interval between x1 and x2 must lie into that convex set. So we've already met one particular case of of a face, that is the extreme points. These are the faces of dimension 0. But you can also consider faces with higher dimensions, for instance, dimension 1. And among the faces of dimension 1, the ones that are bounded only in one direction are called the extreme rays. And the extreme points and the extreme rays are both important because they are used in a theorem, which is a generalization of character-Dries theorem, which allows you to describe the points of convex sets. So any point of a closed convex set with dimension k, which does not contain any line, can be expressed as a convex combination of at most k plus 1 extreme points of C, So that's the regular category theorem. But if you are able to use extreme rays, then you only need k points, each an extreme point of C or a point in an extreme ray. Okay, so let's look at this, this figure here. You see that the points in this triangle, they are a convex combination of three points, E0, E1, E2. But if you're in this area, then the points here can be expressed as a convex combination of only 2 points, one each in an extreme ray, the blue here and the other blue there. Okay, so with this theorem, we can now state the representer theorem for convex regularization. Let's consider a convex function R and m linear measurements that are modeled by this linear operator phi. Okay, and we want to find among all the vectors U which produce the observation Y, solutions which has the least value of R. So if we assume that there is indeed a solution to the problem P, and that the level set, the optimal level set, satisfies some weak assumption, and if the minimal value of the problem is strictly larger than the infimum of the regularizer, then each extreme point of the solution set belongs to a face of the level set of the regularizer with dimension at most m-1. So how is it related to our representation problem? Well, simply by applying Carathéodory's theorem to this convex set of dimension m-1. So what we get is a representation of the extreme points of the solution set as a convex combination of m extreme points of the variable set, or m-1 if we are allowed to pick a point in an extreme ray. So you might wonder why is there this assumption about the value of the problem with respect to the infimum of the regularizer. Well, it turns out that if you have this strict inequality here in the convex regularizer, it imposes some constraint on the relative position between the feasible set, which is drawn in red here, and the level set of the regularizer. They can only be tangent. But if you allow equality there, then they can be in arbitrary position. In particular, it might be that the feasible set intersects the interior of the level set. So it's not really a problem, but it just tells you that you might need one more dimension when the face on which the points lives could have one more dimension. And in particular, you might need one more point to describe the solution. So in the previous example, we only needed 2 points because we lived on a one-dimensional face. The red extreme point here lies on a one-dimensional face, but here it lies on a two-dimensional face. So we need one more point to describe it. So this case, when you have equality, is simply a particular case. Well, it is equivalent to the problem of intersecting a convex set with an affine space of codimension M. And this problem was solved by Dobbins and Lee in the 60s. So let's look at a few examples. We've already discussed the basis pursuit for measures, but let's examine it with our theorem. So the extreme points of the optimal level set, they are the rescaled Dirac masses, where the weight is simply the total variation of the solution. And the dimension, the theorem, tells us that the dimension of the face should be less than or equal to m-1 unless we are facing the trivial solution, which is zero sparse, which is not interesting anyway. So in general, we know that the value of the energy will be larger than the infimum of the regularizer, so we can use this value m-1 as a bound. And as a result, we can write our solution as a sum of at most m Dirac masses. Now, if you look at a feasibility problem, that is, we want to find some non-negative measure which provides some which satisfies some linear constraint, then we can still apply the theorem. But here we are dealing with a set which is not bounded. We have extreme rays that are described by Dirac masses that are weighted by positive weights. And in that case, since we have an energy which is 0 or plus infinity, when you have a minimizer, the energy is equal to the infimum of the regularizer. So we are in the second case. We are in the equality case. We have a bound on the dimension of the face, which is equal to m. So we're able to describe the solutions as m points, since we're picking points in extreme rays. Okay, so here we're using a sum of m Dirac masses with non-negative weights. There is another interesting example that can be looked at in this setting, is the feasibility problem for positive semi-definite matrices. So you want to find a positive semi-definite matrix which satisfies m linear constraints. Well, again, we are optimizing on a cone. The extreme rays are simply the rank 1 matrices that have that form. And since we're dealing with a feasibility problem, we have a bound on the dimension of the face, which is equal to m. So you might expect a representation of the solution as a sum of at most m rank 1 matrices. But in fact, you can do much better, and it's been known in the literature with this formula. And the reason is related to the spectral theorem. So let's remember that if a matrix has rank R, then it can be expressed as a sum of at most R rank 1 matrices. That's just a spectral theorem. And then let's use let's compare it with the faces of the positive semi-definite cone. It turns out that the faces of the positive semi-definite cone are characterized by the kernel of the matrices, the kernel and the images, since one determines the other. And once you have fixed the kernel, you can fix then the image of your, you can fix the value of the matrix on the image, and that's 1/2 times r plus 1 degrees of freedom. So it gives you the dimension of the face that you're living on. And if you plug this into the value of the dimension, you can express the rank using this inequality. So what does it tell us, in fact? It tells us that for convex sets, such as the positive semi-definite cone or its faces, well, Carat-Theodoris theorem is not optimal. You have a dimension, but you don't need d plus 1 or k plus 1 elements to represent the elements of the convex set. But if you think about it, it's quite common, in fact. Let's look at the Euclidean ball. Well, you only need 2 points to represent any point of the ball, okay? And this is an example in the plane, but you could be in an infinite dimensional Hilbert space, you would still only need 2 points, 2 extreme points, to represent any point in the ball. On the other hand, if you look at polyhedras, the situation is different, because there, Carat-Theodoris theorem is optimal. Indeed, except on this Lebesgue negligible set, which is drawn in yellow, you always need 3 extreme points to write your point as a convex combination. Okay, so for polyhedras, Carat-Theodoris theorem is optimal. For more general sets, when you have curvature and so on, then you might do better than Carat-Theodoris theorem. incidentally, you might wonder if this representation theory only holds for these linear constraint problems, and whether you can extend it to more general fidelity terms. It turns out that you can. Well, a first obvious answer is the case where F is strictly convex, because in that case, if you have this energy, you can prove that the solution, all the solutions share the same value of phi u. Okay, so essentially the problem P prime is equivalent to some problem P with a linear equality for some value of phi u. But you can also say a bit more if you only have merely convex functions, but it needs a bit more work. And to see this, well, you can observe that the solution set of your convex problem, which is represented here as S, it's isomorphic to this set S hat here. And what is S hat? It's the intersection of the epigraph of your regularizer with the hypograph of your fidelity term, which is slightly shifted so that they do not intersect with their interior. And again, as I told you before, that it was all about the intersection of a convex set with an affine space. Now it's about the intersection of two convex sets. Can you estimate the dimension of the face of their intersection? And you can do the algebra. It's not very complicated, and you can find some results like that, which bounds the dimension in the solution set. Sorry, which bounds the dimension in the level set of the regularizer in terms of the dimension in the solution set and in the level set of the fidelity term. And again, then you have this representation using Kara-Theodorycles' theorem. So now let's look at the case of functions with bounded variation. So in image processing, for many decades, people have been using this regularizer, following the work of Rodin, Osher, and Fatemi. And this regularizer consists in looking at the total variation of the gradient when you see it as a Radon measure. So informally, you could say it's the L1 norm of the gradient, all right? Or you could define it using this duality formula. So let's consider the very simple problem of minimizing the total variation of the gradient along with the constraint that phi u equals y, where phi encodes some linear measurements that are done using integration against some suitably integrable functions. So, for instance, to fix IDs, let's assume that we have some ideal ground truth that lies in some LD over D minus 1 space. Then we blur it and we sample it. We have M samples and we get this observation. What can we say about the solutions or the extreme points of the solution set for that problem? Well, you might think that this amounts to the theory that Michael has described. Indeed, you're looking at an energy which is the total variation norm in the space of measures, and you have a differential operator. So you might think, okay, well, this case has been settled. We simply have to plug a linear operator in front of the total variation norm, and we're done. But this case is difficult because the operator is not surjective. And that's a crucial assumption. To see how this impacts the extreme points, let's think about the L1 synthesis and L1 analysis balls. They can be very different. For instance, if you have the L1 synthesis ball, if you have a non-surjective operator, then you can recover its three extreme points by taking the intersection with some vector subspace. And you can have very weird things. and its extreme point can be very different from what you have in the usual L1 and L1 synthesis ball. Okay, and here we are in an infinite dimensional space, so it can be even more complicated than on this simple drawing. Still, this problem has been solved in the 50s by Fleming, and he proves that the extreme points of this total variation of the gradient ball are the functions of the form indicator of a set divided by its perimeter. But it's not just any set. You need to look at the simple sets. That is, the sets that are simply connected in the sense of a measure theory. There is also an extension of that result in a paper by Bredis and Carioni in the case of a bounded domain. But essentially, the result stays the same. So let's see how these simple sets and extreme points of the total variation unit ball are related. Well, the key ingredient here is the co-area formula, which is a beautiful formula in the framework of functions with bounded variation. And it relates the total variation of the gradient with the sum of the perimeters of all its level sets. So the first point to observe is the fact that if you have a function that is an extreme point of the total variation unit ball, then this function can only have one non-trivial level set. Otherwise, if you have a function like that, like u, you could threshold it and get u1, and you keep the hat in some function u2, okay? So that u is the sum of u1 plus u2. But if you have written that, you can also rescale things. You can divide things by their total variations, and it gives you weights that are in fact a convex combination. And it's the co-area formula which tells you that these weights are indeed convex weights. And therefore, if you had more than one non-trivial level set, you could find a good threshold so that u1 and u2 have different level sets, and therefore they are completely different elements. And so you would have expressed u as a convex combination of two different elements of the total variation unit ball. This would be obviously a contradiction. Therefore, you can only have one non-trivial level set, and you have the form indicator function of some set divided by its perimeter so that it has a unit, a total variation of the gradient. Moreover, this set, it has to be connected in the sense that if you could write the set as a union of two components, then you can simply write the indicator of E as the sum of the indicator of E1 and the indicator of E2. And then again, you could renormalize things by their total variation, that is by their perimeter. And since the sets are not connected, the perimeter of E is the sum of perimeter of E1 plus perimeter of E2. And this yields an expression of your function as a convex combination of two elements in the total variation unit ball, which is again a contradiction of being an extreme point. Eventually, you can prove that there are no holes in the same spirit. You can write the indicator function of a set that has a hole as the difference between the saturated set and the hole, which I call E2. And again, the fact that you can split the perimeter in that two parts, it provides you with a convex combination which contradicts the fact that you should be an extreme point. So this proves that if you have an extreme point, that it must be the indicator function of some simple set. The converse is also true, but it's more complicated, and it's proved, for instance, in the paper by Fleming or in the paper by Ambrosio, Casillas, Masnou, and Morel. So what is the consequence of describing the extreme points of the total variation? Well, simply, a representation of the solutions. You know that some solutions will be a sum of at most m indicators of simple sets. And therefore, it explains why the total variation tends to provide piecewise cartoon images, piecewise constant images. And it's another explanation of the staircasing phenomenon, although in practice M can be very large, and somehow there is a finer explanation of the staircasing phenomenon that can be seen, for instance, in the papers by Mila Nikolova or Khalid Shadalzai. But it's at least a rough explanation saying that you should see piecewise constant images. So let's look at a numerical experiment. We take 3 measurement functions, indicators of disks, and we impose the value of integrating our function u against all these 3 measurement functions. And the solution is represented here. So we see indeed 3 shapes. And if we look at the histogram, what we see is that you should neglect all the discretization artifacts, but what we see, in fact, is the fact that you have 3 non-zero values on which the histogram concentrates. Okay, that's 3, and not something else. But that should be that is a bit surprising, in fact. Why do we have m non-zero values and not 2 to the m minus 1, which is the value that we could expect if the sets EI were in arbitrary position, if they could intersect, you could have much more values than m. So why m and not more? To understand this, we have to study a bit more the faces of the total variation. Understanding the extreme points is not enough. Okay, what can we say about the faces of dimension k, for instance? So let me mention that this is an ongoing work. It's been paused for a while, but hopefully we will resume it someday. But I can tell you what we know so far. Let me also mention that it's related to 2 very nice books, excellent books, in fact, by Fujishige and Francis Bach about submodular functions on finite graphs. And all the intuition is in these books, but we cannot apply those results straightforwardly because they rely on the assumption that they are in a finite graph. Okay, so all the essential argument between Fujishige and Bach relies on a duality argument. You characterize the polar of the unit ball, and from this polar, then you deduce properties by a duality argument. You deduce properties on the faces of the total variation unit ball. But in our case, we are in an infinite dimensional setting. Everything is continuous. We are not dealing with a polyhedron. So we cannot expect that all the faces are exposed. And we have this one-to-one correspondence between the faces of the unit ball and its polar. And in fact, it's known that for reasonable choices of topologies, some faces of the total variation unit ball are not exposed. Okay, so we cannot, at least I don't know how, we cannot apply this kind of arguments in a straightforward way from these reference books. Still, most essential ideas still hold, but we need to derive them from a different arguments. And to derive them, it's interesting to try to understand the extreme points of a k-dimensional face. Okay, so we know that these extreme points should be, well, no, they are the indicator functions of simple sets. So let's look at the collection E of all the indicator for all the sets, such that the indicator lies in the face. Okay, so this collection should contain all the extreme points and some other sets that are not extremal. And for commodity, I consider this family E plus, so that the positive indicator function lies in the set. And if it's the complement, that is, if it's the opposite which lies in the set, then I take the complement. But it's just for commodity. It's the same as looking at the upper level set of a function. Okay, we only deal with sets with finite measure. So what can we say about this collection? Well, this collection has a nice algebraic structure. It is a ring of set, in the sense that if you take any set in that collection, any pair of sets, their intersection also lies in the collection E, and their union is in E. So you might also refer to it as a lattice, because it provides a lattice structure on that set. And once you have this structure, we can also notice that the perimeter on that collection behaves a bit like a measure, or like a charge, if you prefer. You have this equality, which is the equality case in the submodularity inequality, and which tells you that the perimeter is a bit like a measure. So a consequence of this structural property is the first observation, that if you take any set that lies in the face, or in the collection E, in fact, there is a typo, all the unions of finite intersections of such sets, it also lies in E. Okay, so you have this stability property. And once you have this stability ring of state structure, of lattice structure, what is interesting is to look at the chains, that are the sets that are totally ordered in this collection. Okay, so you look at a chain, E1, E2, E3, and so on. And the first observation is the fact that, well, this collection can only be bounded in cardinal. You cannot not have more than k plus one such sets. And the reason is that these sets, since they are nested, they form a collection of independent indicator functions. Okay, they are linearly independent, and since we have a dimension k in this phase, we cannot have arbitrary many. Okay, so that's very elementary, but it tells us something. It tells us something about the values that the function can take, while the function cannot take more than k plus one non-zero values. Because, and it's not obvious, but you can write it, if you look at the level set of a function, then you can prove that the level set of this function, they form a chain, and these elements, they all belong to the collection E. Okay, so any function should have at most k plus one non-zero values. So once you look at chains, you can also wonder whether there are maximal chains that cannot be extended. Well, it turns out that these chains are the most interesting ones in this ring of sets, because if you look at maximal chains, you can prove that there are different families of chains for a given phase, but all the increases are the same. Okay, so that's what is written here. When you look at a chain, all the increases, the collection of increases are the same, and what changes is simply the order in which you add the sets. So what it means is that eventually the number of sets that you can construct in that way is finite. And again, what you can also prove is that the length of the maximal chain is equal to k plus one. But the important fact is that all the functions are constant on these increments. So you have a partition of the space in which all the functions that lie in the phase, or constant. And it tells you that you cannot build arbitrary many sets like that. And you have this consequence, which is that the collection E, that is a ring of set and so on, it's finite. It has at most 2 to the k plus 2 elements. It's probably not optimal, but at least it's finite. And in particular, the face has finitely many extreme points, and therefore it is a polytope. And if you remember our discussion about the Carré-Théodoris theorem, we are in this situation here. In particular, almost every function that lies in the face f takes exactly k plus 1 non-zero value. Not only it does not take more than k plus 1, but it also takes exactly k plus 1 non-zero value, which explains what you observed numerically. We can also apply all these results to particular cases, for instance, the one-dimensional faces, and to see what happens. Well, you have these conditions of partitions. You also have some notions of decomposability, but I did not talk much about it. But what we should remember is that you have constraints. You could have sets that are disjoint or sets that are nested, but you could not have such intersections on a one-dimensional face. You have similar constraints when the sets have, well, the indicators have different signs, but that's always the same essence. And what is also interesting about this representation of faces is the fact that these faces are related to a tool that was developed in the early in year 2000 and so on by Monas and Guichard and Ballester and co-authors, a tool that was developed to analyze images, which is the tree of shapes. You can organize all the level sets in an image as a tree, which contains the shapes that characterizes the objects that are in the image. And if you look at the expression of the functions that lie on the face of the total variation, well, you can reorder the terms and get this kind of decomposition where the sets are either disjoint or nested. So we have this kind of tree structure plus some conditions on their reduced boundaries, but let's not dwell on that. You have this tree structure on the decomposition of the function that corresponds exactly, if I understand well, to the decomposition of an image in the tree of shapes, so which is a tool that was developed completely in a completely different context for image analysis purposes. So I find it somehow funny. So I will conclude here, and this representation principle is quite elementary. In fact, the main ingredients there are linear algebra and convex analysis, but it can be somehow powerful, at least useful, in the case where you're dealing with infinite dimensional problems. And hopefully this will lead to numerical methods for total variation minimization. My student Romain Petit is working on this topic, and then we can also explore other regularizers, but that's for next talks. So there are two papers on this topic. There is the paper of 2019, and there's a recent note that I wrote about this epigraphical approach, which is a bit more specific, but is the same result. And there was also this paper by Bredis and Carioni, which derives similar results in roughly the same at the same times. So thank you very much for your attention.